Okay, so let's take a look at this. This is meant as a supplemental presentation to for anyone who's trying to read the paper that I'm attempting to write. So my idea is that so my writing is a little bit rusty, and hopefully this will help to kind of iron out the flow of what I'm doing here, what I'm looking at, and what I've done. So as you can see, we're looking at the possibility of attention dynamics emerging as artifacts of what I'm calling perceptual coalition properties. We'll get into what perceptual coalitions are. That's kind of the main hypothesis here, is that attention may not actually be a control mechanism, but rather a shadow of other far simpler processes happening in the background. So let's jump right into it. All right, so in doing this, there were a few purposes for creating the model and the simulations that I did. First, I want to create a mechanistic model that unifies spatial and temporal dynamics of attention. So there's a lot of theory and models that gear towards explaining temporal attention dynamics, and some that are geared towards spatial dynamics. But what is likely the case, and it seems to be kind of a new direction recently, is this idea that there's likely not a mechanism in the brain that controls temporal allocation of attention and a separate mechanism that's controlling spatial allocation. It's probably one system. And so there's a kind of a push right now to unify all these different aspects of attention into a unified theory. There have been a couple that have been proposed that are pretty cool, but I'm going to make some deviations from those. So in making this model, I wanted a model that is biologically plausible, because this is a biological system, and thus it must be evolutionarily emergent as well. There must be a mechanism there by which it could have evolved to come to be. And then 3, we also see a lot of individual differences in attention. So as a result of things like mental training, so you see improved attentional abilities in trained meditators. So there needs to be some kind of a mechanism to explain that, and so I want this model to also be able to provide those mechanisms and be a way in which we can kind of draw hypotheses on why individual differences emerge. So those first 3 are the ones that I had prior to creating the model. And once I created the model, ran the simulations, the outcome of that model, which was much greater than what I had intended. And so the 4th purpose here is something that I've added, and that is to propose a simplistic and mechanistic unified theory of attention. One that might serve as a foundational baseline, a framework upon which we can explain myriad attentional phenomena. And so I believe that I've achieved that here, and I guess it'll be up to you all to decide if you agree, but we'll get into that. So jumping straight into the empirical background, let's start with temporal dynamics. So temporal dynamics are most often studied through the use of rapid serial visual presentation, or RSVP. And I realize that a lot of you will have a lot of background knowledge on the subject, and I'm going to put in this video a table of contents in the description so that you can jump forward if you don't want to go through this, but if you want a refresher, this is just going to be a brief refresher. So looking at temporal dynamics in RSVP, what is most often seen in RSVP is what's called the attentional blink. This has nothing to do with eye blinks. What it is this observed deficit in the ability to report a second target when presented between 200 and 500 milliseconds after a first identified target. So that temporal period there is known as the blink, as if attention itself were blinking and that second target is missed. Now this has nothing to do with the eyes. The second target is seen. It is picked up by visual systems and is processed to some degree in the visual cortex, but it does not reach the point of working memory where it can be reported. So what's causing that? That's a very interesting case. There's a lot of other subphenomena in the attentional blink that make it really kind of difficult to make a cohesive temporal theory of attention. So that would be things like lag 1 sparing. So if you see here, when a second target is presented immediately after the first target in that lag 1 position, there really is not much of a deficit in the ability to report it. So we call that lag 1 sparing. So what's happening there? What's bringing T2 in with T1 when it's presented at that lag 1 space? It's very interesting. More recently, there's been a lot of cases showing things like spreading of sparing. So instead of presenting only 2 targets embedded within a stream of distractors, let's say I show 4 and I show them immediately one after the other. So a T1 and then a T2 in the lag 1 space, a T3 in the lag 2 space, a T4 in the lag 3 space. What will happen is there will be no perceived or no observed attentional blink. They'll all be reported. So there's a whole new thing, another wrench in the mechanism. Increased T2 salience can also attenuate the blink. So if I present a target, a T2 at lag 2, but with an increased salience in the visual field, and that can disrupt this attentional blink, and T2 will be reported. And there's all kinds of studies showing whole report attenuation, increased task demand attenuating the blink. So there's a lot going on. This is one of the most well-studied attentional phenomena there are. And so a lot of theories have come about to kind of suggest or try to explain what's going on here. And the early theories revolved around this idea of resource limitation. The idea that there's limited resources within the brain, and attention is allocating those resources in a beneficial way. And when T1 is identified, so in the case of something like the overinvestment hypothesis, so many resources are allocated or invested in T1, in the identification of T1, that there's this refractory period where attention has to kind of regenerate in order to be able to identify T2. And what we're seeing in the attentional blink is that refractory period of regeneration. That certainly is convincing when you look at the graph, but it doesn't really offer a good explanation of why we get lag 1 sparing. And then once we look at things like spreading of sparing, increased T2 salience attenuation, things like that, this overinvestment hypothesis and resource limitation accounts of the attentional blink really go out the window. And we'll get into that a little bit more later when we start to look at the theories specifically. But a lot of the later theories, they focus on this idea of the attentional blink as a strategy rather than a deficit. And we'll get into that. One metaphor that I'm going to use throughout, and we're going to look at, there will be 3 slides here looking at empirical data, but a metaphor that I want to use is this idea of, imagine for a second that you're looking at a sheet of paper that has a shadow cast on it, and the shadow is being cast from a cube, but you can't see the cube. You don't know that it's a cube. And when you look at the shadow. So there's 6 orientations that the cube can be in that will cast a perfect square, right? Now, you look at the shadow and you see the square, and you can make some assumptions about the item that is casting the shadow. You don't necessarily know that it's a cube. It could be a rectangle. It could be just a flat 2-dimensional square that's casting that shadow. You don't know. But you can draw some conclusions. You can weed some things out. You know it's not a circle. It's not a sphere that's casting the shadow. Now let's say the light source is taken away, the shadow disappears, and the cube is rotated into a different orientation that doesn't cast a square. And the light returns and a new shadow emerges. And now it has all these different angles to it that don't look like a square. Now, there's a few avenues you can go down. You can say, oh, well, maybe it's the same object in a different orientation, but you have no evidence for that. Or you might assume that there's a new object. A new object has been placed in the path of the light. The light was turned on, and now you're looking at a completely different object, right? And that's what I think is going on with these attention studies. And so obviously the object that we're trying to derive the shape of from these shadows, and this would be an example of one of those shadows, is attention. Now, we'll get more into this, but I would argue that RSVP is that perfect square shadow. And it's going to become more apparent when I get into my model in particular. But just keep that metaphor in the back of your mind. I'm going to return to it because we're going to jump to what we're going to do right now is turn that light off. The shadow is going to disappear. We're going to change the orientation of that cube and show you another shadow from a different angle. Okay, so in looking at spatial dynamics, what we're often looking at is attentional shift. So the ability for the focus, the ability of the focus of attention to move about the receptive field, move about the visual field, independent of eye movement, right? Now, this is a disclaimer. Of course, there are tons and tons of studies that have looked at temporal dynamics and spatial dynamics. I've picked some big ones as specific examples. This presentation would be 2 years long if we went through all of them. So I've picked some of the big ones that have been really foundational in the field. So when looking at spatial dynamics, kind of the keynote study is Michael Posner, 1980, looking at attentional shift. And the way that they did this is by asking participants to respond to the presentation of a target stimulus somewhere in the visual field, right? So a target appears, and once that target appears, they're asked to press a button. And the reaction time is recorded. Now, the experimental conditions here are, in some trials, a valid cue was presented prior to the presentation of the target. So a valid cue means that the cue is presented in the spatial location that the target will be presented in. In invalid cases, a cue would be presented prior to the target, but that cue would be in the opposite location of where the target would show up. And then you have neutral cases in which there are no cues. And so what we find in that is pretty intuitive. In cases where a valid cue was presented, reaction time was reduced. And in cases where an invalid cue was presented, reaction time was increased, and this is all relative to the neutral case, right? So what we can interpret from this is that, with an individual focusing on a central fixation point, and when the cue is presented, the focus of attention, this spotlight of attention, shifts to the location of the cue. When the target is presented to the location of that spotlight, reaction time will be less. And the reason why reaction time is greater in the invalid cases, it takes longer to react, is because there's that added work of moving the spotlight of attention from the location of the cue to the location of the target, and that translates to an increased reaction time, right? That all makes perfectly good sense. Again, I'm going to go back to that cube metaphor, in that the light has been turned off, the cube has been shifted, and then the light has been turned back on, and we're looking at a wholly new shape. A new shape has emerged in the shadow, and we're left wondering whether we're looking at the same object. And I think for the long history of studying attention, we have treated them as two separate objects, right? So we have our temporal dynamics and theories that explain temporal attention, and we have our spatial dynamics and our theories that explain spatial attention. And we've been looking at these shadows separately without really good assurance that we're looking at two shadows of the same object, just in different orientations. And so here's the reason why I'm using this metaphor, is the next study, this final study that I'm going to show you, does a good job of blending both spatial and temporal, and it's as if the orientation of that cube was moved and the light never turned off, right? So now we know we can see the rotation happening, and we're looking at the same object in different orientations, right? So that's the reason why I'm using this metaphor. Let's jump into that third study, and we can see exactly what I'm talking about. Okay, so we talked about temporal dynamics using RSVP, and then we talked about spatial dynamics looking at attentional shift. This protocol, dual stream RSVP, really brings both into the experiment. So what's happening in dual stream RSVP? Well, just like in RSVP, there'll be a stream of characters, so targets embedded within distractors. But in the case of dual stream RSVP, there's two streams of this happening simultaneously, adjacent, in the spaces adjacent to a central fixation point. Now, they're close enough that eye movement is not needed. Eye movement is not an issue in this study. But you have the possibility now of different experimental conditions. So there are, in studies like this, you will have same stream and different stream trials. A same stream trial is where target 1 and target 2 are presented in the same stream, right? And as you might expect, when that happens, you get a pretty standard attentional blink, where you see lag 1 sparing, you see a pretty severe deficit out towards lag 2 and lag 3, and then you get recovery out towards lag 5 and in this case lag 9. So that's in the same stream. Now, what's interesting is in different stream trials, and that's where T1 and T2 are presented in the opposite streams. So what happens there is instead of seeing lag 1 sparing, we see lag 1 deficit. So it's really interesting. Why is that happening? There's a lot of really good interpretations. Jeffries, 2017, check it out. It's a great set of experiments. And basically the interpretation there is that the attentional spotlight has moved and focused on the stream containing T1, right? And now when T2 is presented in a different stream, just 100 milliseconds, and they did a lot of different SOA trials, but we'll focus on 100. When T2 is presented to the other stream only 100 milliseconds after the first, that attentional field has focused and moved to the other side, and it's presented outside of the focus of attention. So that's why we observe lag 1 deficit rather than lag 1 sparing. Another super interesting thing that's going to be important in my model is lag 0 sparing. And I believe that's Bay and Weibel 2014 looked at what happens when you present 2 targets simultaneously in different streams, right? Absolutely brilliant to think to do that. And what happens is both will be reported by the subject. So instead of lag 1 sparing, it gets moved back to lag 0 sparing. So the interpretation here is that at the point of target presentation, that visual field, that attentional field, is wide enough. The focal width is wide enough, and we'll get into focal width, but it's wide enough to encompass both streams, and therefore does not exclude either of them, either of the targets that are presented. So it's kind of interesting. It's bringing in that temporal nature, the temporal dimension of that spotlight moving and focusing around the visual field. That's going to be really important in the model that I've created. So these are the 3 main empirical studies that I wanted to highlight. Of course, there's tons more, but these 3 are going to be very important for the creation, the simulation, and the interpretation of my model. So now that we've got that out of the way, let's jump into the theory and have a look at what's going on there. All right, so now we get to jump into what I'm really interested in, and that's a theory that explains, or that's presented to explain how we get these temporal and spatial dynamics of attention. So we're going to jump real quick into my favorite here on the temporal side, and that's the episodic ST squared model. We'll jump into that one. It's a very interesting computational model of the attentional blink. And then we can get into some more theoretical models of spatial attention, how attention moves about the visual field. We'll talk about specifically the zoom lens model and the spotlight model of attention. Both of them are very, very similar. And then we're going to get into some overarching theories on how what feeds attention, what's going on to create these attentional dynamics as far as inputs go. And so that's when we'll jump into the bias competition model, and then an offshoot of that, the integrated competition hypothesis. And then we're going to leave attention altogether and jump into some other theory that I think is very useful for what we're doing here. We're going to talk a little bit about evolutionary game theory as it pertains to perception. And then we're going to jump into consciousness studies a little bit and talk about the neural correlates of consciousness and a framework for identifying those neural correlates of consciousness that Francis Crick and Christoph Koch put together in 2003, shortly before Crick died. It's going to be some pretty interesting stuff. This is definitely an area of the presentation I wouldn't skip. But yeah, let's jump right into it. All right, so looking at theories of temporal attention, there's one that really stands out amongst the crowd, and that would be this episodic ST squared model. It's built off of their previous ST squared model, and that stands for a simultaneous type serial token model. And what this model was initially built to explain the attentional blink. How does the attentional blink arise at a neuronal level, in a mechanistic way? And the initial model, the ST squared model, was excellent at doing that. But some new data came out that kind of wasn't explained by the ST squared model. It didn't jive with the ST squared model, and that was things like spreading of sparing. And that's and we covered that a little bit earlier. That's the situation where if multiple targets, say 3 or 4 targets, are presented in direct succession to each other, so immediately following the previous one, there will be no attentional blink. And in fact, nearly all of those targets will be brought in with T1 and will be identified. there are some things that happen there, and what you get is there's a cost. There's a cost to that sparing, in that the temporal order of those reported targets is often jumbled, right? So they'll be able to report the correct targets, but they won't report the correct order. And that actually happens in lag 1 sparing as well, not just in spreading of sparing. So why does that happen? So Weibel and team had some really ingenious ideas about why that happens. And if it sounds like I'm a fanboy of this particular model, it's because I am. I've been reading about it since 2009, and you'll see a lot of influence from it in the model that I've created. So basically, what they have arrived at is that the attentional blink is not a deficit. So it's not the result of a resource limitation. It's not the result of a failed adaptation to rapid temporal targets. Instead, it's a cognitive strategy. So somewhere in that handoff between attention and working memory, there is a limit in there's a limited ability to correctly bind these types into working memory and what they call tokens. And so in their model, you have types, and so that might be a digit or a letter or something, and that gets identified, and it gets bound to a token in a binding pool, and that token represents a serial position in temporal space. So when T2 is presented at lag 1, it goes into that binding pool. It enters into that binding pool with T1, and oftentimes will bind to a token prior to T1 fully binding to a token, and that's where you get your order switching. So now we're leaving attention a little bit, and we're jumping into working memory in that encoding phase, the second encoding phase. When it comes to the actual attention portion, this input phase, the selective portion of the network where you get your selective attention, what you have is this regulatory circuit called a blaster. And I don't have anything as cool as a blaster in my model. That's really just an awesome name. So that's something that I need to address. I need to get something cool like a blaster. But, and I'm not joking, that's pretty awesome. But anyways, this is a regulatory circuit that's basically controlling the start and end of what they call attentional episodes. And why do we have attentional episodes? Why is attention episodic? Well, that's where the strategy, the cognitive strategy comes in. So because of this limited ability to bind types to tokens and the possibility of errors in that binding process and troubles efficiently binding types to tokens in that binding pool, what this blaster does is it creates episodes. So once a target is identified, it triggers, let me back up. A target is identified, and once there is a gap, so if T1 is presented and then at lag 1 no target is presented, that absence of the target triggers the episode. So basically it's like attention is saying, okay, we got what we need, let's shut everything down for a while so that we can bind this target effectively to a token. And then once that happens, then we can discontinue that episode in preparation for another episode, right? For the next target. And that's where you see the attentional blink come into play. How this explains spreading of sparing is because there is no temporal gap after a target. And you could say you get a stream of 4 targets. Because there's no temporal gap there, no episode is triggered. So the triggering of the episode actually happens at that gap after a target is presented. It's pretty interesting. Does a great job of explaining why you get that spreading of sparing, why you get lag 1 sparing. These are the harder things to explain in the attentional blink, in temporal attention. Really, those are the things that make the puzzle fun, and they've done a really good job of explaining that. This is a very inspirational model. My model will deviate from this quite a bit, but there's some main things that I've taken away from this model and put in my back pocket that are important, not just for temporal attention, but also in the spatial realm as well. So the big thing here, that the big takeaways that I want you to keep with you throughout the rest of this presentation is that attention is segmented temporally, right? So in this case, we're talking about episodic distinctiveness. Attention occurs in distinct episodes, and that really that's pretty fundamental here. This is very important. Numerous studies show this, and it kind of, William James said, attention is a river, right? So it's a stream. Well, no, sorry, William James. It's not. It's episodic. It occurs in episodes or frames or there's some kind of segmentation to it. And then the other big thing is, let's throw away this idea of resource limitation. I don't like it. It doesn't make sense to me, and we're going to put another nail in that coffin later. But really, I want to move away from this idea of attention as a deficit, or attention as a mechanism to make the best of a bad situation, right? So those are the big things here. Let's now switch gears and jump into the spatial realm, and see what kind of interesting theories we have there. All right, so when we're talking about spatial attention, we're talking about how the focus of attention moves about the visual field, right? How much of the visual field does it encompass? How many things can be presented at once, or can be detected at once? So going back to 1980, Posner, classic study, he looked at the results. He had his valid cues, his invalid cues. He's looking at reaction times, and he suggests a spotlight model of attention. So what does that mean? He imagines that the focus of attention moves about the visual field independent of eye movement, and that when a stimulus is presented to the visual field, if it is not presented within that spotlight of attentional focus, then that spotlight must move to the location of the stimulus for the stimulus to be processed, right? Makes sense. Perfectly meshes with the data that he was seeing. Well, let's flash forward to 1986. Erickson and St. James at U of I believe, they refined this model, and they first agree that yes, attention moves about the receptive field like a spotlight, but there are more dynamics in play. So not only does it move about in its spatial location, but the focus of attention can expand and contract, much like a variable focus lens. And what they derive from this is that attention acts like a zoom lens. So we have these multiple dimensions in which multiple spatial dimensions in which attention can move about the visual field. So in its actual location and its variable width, the variable width of that field. That's going to be really important in this model that I've created. It is one of the things that I've simulated, and it becomes very important when we look at hybrid tasks that, like we saw with dual stream RSVP, where we have a temporal aspect, so RSVP, and then we have a spatial aspect, two visual streams. So yeah, those are the big takeaways there, and that's going to be important when we talk about attentional focusing. So the focus width is variable in both the attentional focus is variable in both its spatial width and its focal location. Cool. So now we have we have a very, very good theory for temporal attention. We have a very good theory for spatial attention. We're going to have to put those together somehow to unify these concepts of attention and unify these dynamics into a single model. So let's jump away from looking at temporal and spatial attention. Let's just look at attention in general. Let's look at some theories that explain some more general aspects of attention. All right, so backing up and getting a little more general here, what I'm really interested in now that we've kind of looked at the specifics of temporal and spatial, is what kind of inputs feed into attention or to attention networks or systems or whatever they might be to influence the outcomes, right? So we know at any point in time you're not actually able to report everything that's in your visual field. Now your eyes may be taking in all of the light that's there, theoretically. We know that's not completely true either, but we'll say, just for the sake of argument, your eyes are bringing in all of the light presented to them in the visual field. Now there's some kind of a, Mary Potter, Chun and Potter, 1995, talk about a two-stage model of attention, where this first stage, everything is processed, and a second stage, only a select few things are processed at the level of working memory. So what's happening between those two stages, and what is influencing that outcome? What decides, what gets to pass into the second stage and what doesn't? So back in the mid-90s, you have the biased competition model. And three basic principles here. One, visual representation is competitive. Obviously, there has to be some kind of competition there. That's where selection comes from, right? There has to be some form of competition. Visual percepts are competing for representation in working memory. So that's our first principle there. It's an important one. It's going to be huge in my model. It's pretty intuitive. The second principle here, this competition is influenced by both top-down and bottom-up mechanisms. That's huge. It's very intuitive. All you need to do is take a couple seconds for introspection, and you'll know that there are factors internal and external. So endogenous and exogenous controls or influences on what you are actively attending to at any point in time. And we will get into that more in this model. And then 3, competition is integrated across brain areas. What they mean there is that attention doesn't occur in one particular area of the brain. Activity from all across the brain is involved in this competition, and that competition is integrated. So we can jump from there into the integrated competition hypothesis, and we have 3 more basic principles, right? So vision is processed in many systems, and object representations within these systems compete. Again, this is pretty intuitive stuff. This competition is then integrated, and the competition can be directed based on object featural properties in a top-down manner. So that last one, I included that because this last principle here. And when we look at top-down influences on attention, and studies that have been done describing top-down influences or exploring top-down influences, it's most often in the spatial realm, the location-based realm. But it must also be in an object or featural manner. So there's just not a lot of research on that, but it is coming along. And the model that I've created should provide a mechanistic explanation of how that works, and that it is likely, in most cases, equally potent to location-based top-down influence. That's going to be big. And of course, those are my takeaways here. The big things to remember is this top-down and bottom-up influence on attention to bias this competition between objects and location representations, and then getting into this object featural top-down activity is going to be huge. All right, so now we're going to leave attention completely. So for those of you that are super familiar with attention, and this has all been super boring so far because you've read it all a million times, this might be a segue into some new stuff that that maybe you haven't seen. And this is kind of getting back into my roots in biology. It's combining my two favorite things, biology and theory. So let's jump into that. All right, so now we're looking at evolutionary game theory as it pertains to perceptions. And this is a super interesting study. I recommend you go read it. It's not too math intensive. They do a really good job of explaining it. But basically, these folks were looking at evolutionary game theory and the kind of predominant hypothesis that the more veridical a representation, the more complete a representation of an external environment that perception creates, the greater the fitness advantage. And so basically, if you look at the predominant ideas in neuroscience, cognitive science, as far as natural selection goes, all species on the planet should be just progressing towards perfect and true perceptual recreation of their environment. So what they did here is they ran a series of simulations. Basically, they took two strategies. One was a perceptual strategy geared towards veridical perception, so a holistic recreation of an agent's environment. And the other strategy was one geared towards utility, where only the important things are seen and maybe even sometimes embellished a bit, or you might say hallucinated, to accentuate utilitarian things in the environment. And what they found was that the utility-based strategy would endow a greater fitness advantage and would drive veridical perception to extinction. So what this suggests is that in many cases, it is more beneficial for perception to be geared towards utility rather than veridical perception. And why is this important in terms of what we're doing here? Well, so many theories have been based on resource limitations. So many theories of, in particular, the attentional blink are based on limited resource accounts, right? Well, that doesn't really fit with evolutionary game theory, right? So rather than attention arising as a mechanism to direct limited resources, perhaps attention is an outcome of this utilitarian strategy. And this makes sense. It's pretty intuitive that that's what attention is doing, but it's the why attention is doing it that is important to me here. We all know that attention is selecting the most important things in an environment, and that has utility imbued in it. But it does not seem likely to me that that is done out of necessity of limited resources, but rather that it is more likely that we have plenty of resources, or we have greater resources to process far more than we actually do, but that doesn't create a fitness advantage, right? And we'll get into that a little more later. But I'm going to use some analogies here. You can look at perception in two ways. So either perception is a construction worker building a building out of bricks, right? So they have a certain amount of bricks. They're trying to build a building or copy a building, but they have a limited number of bricks. And so what you get is a limited recreation of what they're trying to build, right? Just because they have limited resources. Or you can look at perception as sculpting from a block. So let's say there's a block of marble and trying to recreate a structure of in some way, and you have plenty of resources, so the block is bigger than what you're trying to create. You have plenty of resources to carve away and make a perfect representation, but that perfect representation is not utilitarian, right? And it doesn't create an advantage. So instead, what the sculptor does is sculpts a utilitarian recreation of an object. So those are kind of the two approaches to perception, and the model that I've created and the things that we're going to talk about down the road favor that latter interpretation. So a sculptor instead of a builder. And I'll get into more why I think that way and why I think my model suggests that. All right, so we're going to leave biology now. We're going to jump into consciousness studies and look at some interesting theory from 2003. So when looking at consciousness studies, Francis Crick and Christoph Koch in 2003, they suggested a framework for consciousness. And what they were talking about there is finding the neural correlates of consciousness. And then once we find those neural correlates, we will be able to then solve the hard problem, if indeed there is a hard problem of consciousness. And that's, what Crick referred to as the astonishing hypothesis, right? Great book if you ever get a chance to read it. He's a very interesting guy. But we're not talking about consciousness here in this presentation, but there were a few things in that paper that stuck out to me. And I was fortunate enough to read the paper after I had created the model that we're going to go through. And I think if I had read the paper prior to, I would have just dismissed it as, oh, that's interesting. But because I read it after I created the model, I saw a lot of the things in my model represented in this paper, and it certainly made sense. So the two things that they talk about that stuck out to me are essential nodes and coalitions, right? So what are essential nodes? They're the basic neural unit needed to become aware of an aspect of a percept. So in other words, if you want to, say, in my model, if you want to represent the digit 3, there must be an essential node that represents the digit 3. And that is a column of neurons within my model. And in the paper, they say that these are likely embodied as cortical columns, right? So it's very interesting. So if that cortical column is eliminated, the model can no longer express the digit 3. So yeah. Now, what happens when you have a bunch of these nodes firing together, and bear in mind these nodes, these cortical columns, are highly interconnected, and that meshes with a lot of the neurobiology that shows a high degree of interneurons interconnecting these columns in the cortex. So what happens when you get a bunch of them firing together? You get coalitions. These are assemblies of active essential nodes, right? This concept goes back to Hebb in 1949. So Donald Hebb dedicated an entire chapter in the organization of behavior to these assemblies. And these assemblies, the formation of these assemblies, the connections between them are built on, Hebbian style learning. And what happens within them is active nodes excite other nodes, right? So they've learned a pairing, so they're grouped in some way. And in my model, I'll show you how that grouping works, but they're grouped in some way. And so when one becomes active, it excites other nodes within the coalition. And then the big important part is that it inhibits, active nodes inhibit nodes that are not within the coalition. And that's really what defines a coalition. So what are the defining features of these essential nodes and coalitions? So first is assembly, right? So nodes of a coalition amplify the representation of other nodes in the coalition, right? And that's the first. So assembly is really, competition feeds into assembly, right? So coalitions are highly interconnected by inhibitory projections, and this facilitates heavy competition between coalitions, between nodes. And then a winning coalition will carry information that achieves conscious awareness. That's pulled straight from them. If an item, if a stimulus or a group of stimuli are to be perceived consciously, so now we're getting kind of into that phenomenology, they must be a part of a winning coalition. Now these coalitions would be very transient. They would, rise and fade away quickly, making way for others, constantly competing with each other. In my model, and you'll see the assembly of a coalition is more defined by that lateral inhibition, which is facilitated by these inhibitory interneurons within my model. So the definition of a coalition is based more on what it excludes rather than what it excites. And we'll get into that. And we're going to expand on this idea of essential node coalitions. He did a great talk with the Society for Neuroscience shortly before he died. Definitely recommend listening to that. It's on YouTube. I'll post a link in the description here. But yeah, so let's jump forward. So while the paper from 2003, this Framework for Consciousness paper, was extremely interesting, it wasn't particularly geared towards attention. This is geared towards consciousness. But because it's so useful for attention, at least in terms of the model that I'm proposing here, there are a lot of things missing. A lot of things missing in terms of defining a coalition. So let's first identify what's missing, and then we'll fill in the gaps in a little bit here. So how do we define the coalition in terms of attention? And I believe attention to be the kind of the birthplace of these coalitions. So what are the structural components? How do we define exactly what a coalition is? How does the coalition assemble? What dynamics are in play in the life cycle of a coalition? What is the life cycle of a coalition, right? And then what inputs feed the structure and dynamics of a coalition? Now, if you look at these questions in terms of coalitions, and you look at the theories that we just went through, we can draw a lot of answers to these questions already based on the first half of this presentation, right? And that's really what I saw when I read this paper. So we're going to put it all together. We're going to kind of flesh out this idea of coalitions. And in terms of attention, what I'm calling these are perceptual coalitions, right? So they really bridge that gap between the stimuli input, the photoreceptor phase, the visual processing phase, and working memory, right? So I based on what I've modeled here, I believe that if you look at the two-stage model from Chun and Potter in 1995, if you identify that point between stage 1, where everything is processed, and stage 2, where only select things are passed off to working memory, if you identify that point, what you will find are these perceptual coalitions. And we'll get into exactly what they are now. So this is a diagram that I made to explain this concept of perceptual coalitions. We're starting to get into my own stuff here, so put on your skeptic glasses, and please, if you have any feedback on gaps, things that I might not be seeing, please let me know. But what's really interesting is, so when I first set out to identify a common structure, a common dynamics between temporal and spatial attentional outcomes, right? So what's the common root of those two? I tried to find this kind of metaphorical code. There must be some kind of a code, a language that creates these two outcomes from the same source, right? And this is really what we're looking at here, is what I modeled from the beginning. It wasn't until I read that paper by Crick and Koch that it really helped me to formalize those ideas, to formalize that code under this idea of coalitions, right? And so let's jump into it. Now it's going to be immediately apparent because I'm gonna outline it here. But if you looked at this diagram without listening to me blabber, you would see pretty quickly why it's important that I went through the bias competition model, why I went through the zoom lens model of attentional focusing, and why I went through the episodic ST squared model, right? So they're all going to be represented here in some way, shape, or form. Now I've altered them in certain ways, but very little. So really, I mean, truly standing on the shoulders of giants here. This is really like putting together a puzzle. I didn't paint the picture. I just put together the puzzle here, and hopefully in a way that is coherent. So again, we have top-down and bottom-up bias forming this structure that we call a perceptual coalition, right? So top-down might be task relevant activation. Maybe emotional valence is, well, we know emotional valence affects attention. Learned associations, that's where we're getting into Heb and looking at these assemblies. From bottom up, that's just going to be stimulus-driven activation. So things like salience within a visual field is going to play a big part in this. And again, that's going to be modeled and simulated in my model. So that's kind of our bias competition model there, right? Now let's get into the actual perceptual coalition. Now the coalition is divided into two structural dimensions. We have an object dimension and a location dimension. So you might think of this as the what and the where. And when I was thinking and doing a lot of contemplating on how we can achieve spatial and temporal dynamics, what are the two important what are the important aspects of that to create that? Do we need a time dimension in there? No, I don't think we do. I think we can achieve all spatial and temporal dynamics of attention with these two structural locations. So attention attends to objects and to locations. We can do everything with that, and we'll get into why I think that, and then why the simulation shows that. Now, this is where it gets important. I think other theories have looked at object and location for attention, that attention attends to objects and locations. They've looked at that. But the reason why we're missing out on so much and we're not able to unify attention is because we're not going one layer deeper and looking at the dynamics. So we have two structural dimensions to a coalition, and then within each structural dimension, we have two dynamical dimensions, right? So there are two main dynamics independently feeding these two dimensions, right? So let's start with one that's pretty darn familiar to us at this point, and that is the focal width of the attentional spotlight, right? So exactly what we were talking about in the zoom lens model. The location dimension is variable in its focal width, right? Now it's also going to be variable in its location, but that is part of we think of that as the structure. You have a temporal dynamic of this spatial focusing. So this attentional spotlight can expand and contract and move. We know that. There also must be a temporal dynamic to that expansion and contraction and that movement. There is an attentional dynamic that controls that location structure, right? So at any point in time, a dominant coalition will be focused on one location, theoretically one location, with a set focal width. There is a temporal dynamic to how long it can hold that focal width and how long it can hold that location, right? So those are the two dynamical dimensions of this structural dimension. Now, here's where we're branching out into new and interesting stuff. We're going to take that zoom lens model and we're going to apply it to the object dimension. And so I would argue that there is a focal width of featural specificity, right? And this meshes with Gestalt principles of grouping, right? So the focal width of featural specificity isn't actually a spatial width. What it is it is a categorical width. So let's take, for instance, in a classic attentional blink studies, you have letters and digits. Now, letters and digits are both held within the grouping of characters. They're both characters, right? Now, that's a very wide focal width of featural specificity. We can zoom that focal width in to include only digits, right? And within digits, you have 1, 2, 3, 4, 5, 6, and so on. Now, we can focus that even more down to the number 3. So what you get here is this variable focal width of featural specificity. And I would argue, just like in the location dimension, there is a temporal dynamic of this focusing. So how long does it take for this featural specificity to focus on the digit 3? And how long can it hold that? And how do those top-down and bottom-up biases influence that temporal dynamic, right? So when you add all of this together, you get a perceptual coalition, right? And no two perceptual coalitions are alike, and they are very fleeting in their existence. So they might exist for 250 milliseconds in my model, and I think a lot of experimental data suggests that 250 to 500 milliseconds is pretty regular. That's probably the average coalition time duration. But we know that in terms of interpreting attention as perceptual coalitions, these coalitions can be very long-lived in cases like inattentional blindness, where heavy task-relevant activation is biasing these temporal dynamics and holding this focal width of this featural specificity onto the basketball, so that the stimulus-driven activation of the gorilla does not override that particular coalition. We'll get into that more and simulate all of this. This is super interesting. I'm very excited about this. So, but yeah, so let's jump forward and do a little brief intro on how I simulate this dynamic in a connectionist model, which is, to me, a ton of fun. So we're going to try to make sure that anybody watching this will understand the dynamics of the connectionist model. It's really not that complicated. So let's jump into that. So when modeling all this, it's very important to remember that these structures and the model that I've created is completely arbitrary, right? I wasn't looking to create a neural network model that I thought was anatomically correct, right? What I'm trying to do here is create structures that simulate these dynamics, if that makes sense. So don't look at this as, oh, that would never happen in the brain, right? I don't know how these dynamics happen in the brain, but I want to show that these dynamics are, one, extremely simple, which lends to biological plausibility. Two, there are no control mechanisms required to create these complex behaviors. And three, that these dynamics are implementable. They can be implemented in a very simple environment, and then again, that lends to biological plausibility. If I can simulate these dynamics here in this simple platform, the SimBrain platform, it seems very plausible that they can be elicited in the brain. Another thing to remember is that within my model, all of these units are, for the most part, identical. Now, there are some areas, some units in which I have, for instance, slightly altered the decay coefficient. So all of these neurons have exponential decay functions embedded within their activation functions, and I can change the coefficient of that exponential decay, which, and I'll get into that later, that lends again to biological plausibility. It seems like an excellent avenue for natural selection to tune models over, or to tune networks over time. But anyway, so let's jump into it. I'm going to start with this network on the right. And this is what I call a focusing network, right? And this would kind of be comparable to inhibitory interneurons in the cortex. And so what you see here are, and let's go and let's talk about this in terms of spatial location. So let's say this is a spatial focusing network. This is really the item, the structure within my model that creates the zoom lens model, right? So that whole complicated process of focusing in the attentional spotlight can move about the visual field and can expand and contract in its size. Something that complicated can be explained with a structure this simple. And what I'm showing here is that this can be scaled to theoretically infinite number of units. So let's say that this grouping 1 represents the left side of the visual field, grouping 2 represents the center of the visual field, and grouping 3 represents, or N here represents the right side of the visual field. So what we have are what I call focusing exciter nodes and focusing inhibitor nodes. So a focusing exciter will receive input when essential nodes or coalitions in its area become active. So that activity feeds this exciter. That exciter then feeds all inhibitor neurons not associated to its own area of the visual field, right? And then what these inhibitors do, these focusing inhibitors, they then feed forward to inhibit gate units within their own, and we'll get to gate units here, within their own visual field, right? So this is just a simple way of one visual area, an active area of the visual field, to exclude activation in other areas of the visual field. And what happens is there's a focusing of that attentional spotlight. So if none of these are receiving input, or if they're all receiving equal input, what will happen is the focus of attention will include the entire visual field. But once, let's say, a target is identified in visual area 1 here, it will rapidly suppress any inputs in other visual areas, resulting in an attentional focusing on visual area 1. And you'll see I've done a model demo, and because of the awesome capabilities of SimBrain, this is really a great teaching tool. If you have students that are having a hard time grasping neural dynamics, get them on SimBrain, because it's like Legos for psychologists. It's amazing. But I've got a demo on this, and I'll let you know a good time to pause this presentation and go look at the demo. But so these focusing networks are used to focus both in the object and location dimension of the coalition. So let's just come back here. You have the object dimension and the location dimension. These focusing networks are used in my model to accomplish both tasks, right? Now, coming over here to the left side here, what we have here is a structure that is specific to object focusing. And again, remember, these structures are arbitrary, but I was trying to model dynamics rather than anatomy. So one of the principles of to achieve this kind of Gestalt grouping at a finer level, and I could have used focusing nodes to go even, or focusing networks to go even deeper here, but instead I used these. What I did was I grouped items by type. I call this a type bundle, right? So let's say all of the objects bound together in this bundle represent digits. So this would be the number 1, the number 2, all the way out to theoretically infinite digits. I mean, you would only need, 10, 0 through 9. But they're bound together. And the way that they're bound together is not through lateral connections. So there's no lateral inhibition like you would see in the episodic ST-squared model. Well, what you have is this, and you'll see it's kind of blaster-like, right? But it's a modulatory pair is what I call it, and it has an amplifier and a suppressor unit. And you'll see that the amplifier unit amplifies these gate units, and the suppressor unit inhibits them. So what happens is input is presented to the network to these gate units, right? When a gate unit is activated, it then feeds forward to activate what I call a detector unit. Now these detector units are super interesting, and what they do is they feed into these focusers, right? So a detector detects activity in the gate and feeds into a focuser, which then inhibits other locations, right? But what it also does is it feeds into these amplification units and these suppression units. Now, what that does is it provides an initial boost to these gate units. And that's kind of that assembly phase of coalitions, and that nodes within a coalition will activate like units, right? So detection of the letter of the number 1 will activate other objects within that type, right? Now, if you've ever done neural network modeling of any type or mathematical modeling, you'll see it immediately. Let's say the suppression unit wasn't there. You have gate, activating a detector, activating an amplifier, activating a gate, right? So any input to this gate is an attractor state. This is an endless loop. It will become fixed, and we know that that doesn't work for a model of attention. It can't be fixed, right? So what I did was added this suppressor unit, which acts a little bit slower than the amplifier unit, but is a little bit more powerful. And so what that achieves is a further degree of object focusing to that lower, that more specific number. So what happens is you get an initial boost in these gate units, and then the suppressor unit steps in and suppresses these gate units, kind of stops that attractor state, and that now you have a coalition that is focused in the object dimension on that specific number, not just on the type anymore. And that's a hyper focused coalition in that object dimension. And so what that does is block these. And in this model, that's where we get an attentional blink. You get lag 1 sparing. That's all occurring in here. Now it will interplay with some of these focusing networks, and I think my next iteration of this model will eliminate this modulatory pair and just add focusing networks tying together these types. But for now, this very adequately simulates these principles. And again, I encourage you to watch the demo, and this will all make much more sense in the demo, and you'll see how these interact with each other. So again, you can see how simple this is. There's really no magic or voodoo to it. There's no there's no boss here. There's no supervisor that controls, the allocation of attention. There really is no allocation of attention. Attention is not a mechanism in this model. Attention is an outcome. in this model. And again, we'll get into that deeper. It's a really interesting concept that I think is fairly powerful. So let's jump forward here, and we've created the model now. Now we need to run it through simulations. So let's go through that. So with this model, I simulated 3 classic experimental protocols. They might look familiar to you. We went through them earlier in the presentation. So I picked these for a reason. I could have done a lot more. And in the paper that I'm writing up, the draft that I have, I go through a lot of speculation on how other experiments can be explained in the light of these perceptual coalitions. And it's intuitive to the point that they almost don't need to be simulated, but I do plan to simulate them, because I've learned what I have cooking upstairs doesn't always make sense. So these simulations help. But the reason why I picked these experiments, these protocols, is to isolate the different aspects of these coalitions, right? So RSVP is great for isolation of the object dimension, and that's because the spatial location is a constant. So you have a single RSVP stream at a fixation point. We have eliminated that spatial dynamic, so we can look at the life cycle. We can understand the assembly, the competition, and the decay of the object dimension of a coalition, right? Because we're keeping the location dimension a constant. It's not that it's not there, it is, but it's a constant. It's held at one location. There's no location-based competition in RSVP. So that's experiment 1. Experiment 2, we jumped into the spatial queuing task, right? We're looking at reaction time in response to valid cues, invalid cues, all that good stuff. The target identity in that experiment is a constant, right? It's not that it's not there, but it's a constant. So the object dimension is fixed throughout this experiment. So what that allows us to do is isolate the location dimension of the coalitions and understand draw conclusions about the dynamics, the assembly, the focusing, the temporal dynamics of focusing, all of that good stuff can be isolated in this experiment, and we can look at that and really understand that location dimension. Then experiment 3, dual stream RSVP, it has components of both. So this allows us to look at the entire coalition in both its object and location dimensions, morphing and interacting with. So really what we get to see, which is so cool in experiment 3, is we get to see the formation of a coalition in response to target 1 in one spatial location, and then we get to watch the death of that coalition as a second coalition in a different spatial location takes control, right? And we get to see what the temporal dynamics of that are, because we're presenting T2 at different temporal locations in relation to T1. So we get to really isolate, or really analyze what's going on there. So jump forward to the results. I'm not going to bore you too much with this. And again, the demo does a really good job of showing what's actually happening here in these experiments and how I simulate these. It might not seems kind of odd, how you could present, how do I run a computer through RSVP? It's actually very, very simple. And then I go through that in the demo. And maybe it'll whoever's watching, if you're interested in pursuing these kind of things with experiments that you're doing on people, might give you ideas on how to run these experiments on a model and generate hypotheses. And really, having this model has given me a lot of ideas for new experiments that haven't been done yet, and I can run the model through those experiments and generate hypotheses on what I expect humans to do, which is super interesting. This thing could keep me busy for a lifetime. So in experiment 1, so a clear attentional blink was observed. plain as day, it's there. Lag 1 sparing is distinct. It is a thing that is brought in with this model. Increased T2 salience attenuates the blink. Absolutely. So if I increase the input values of T2, say when it's presented at lag 2, it attenuates the blink phenomenon. And then also not listed here is spreading of sparing. Spreading of sparing is also brought in, and we'll get into why spreading of sparing and lag 1 sparing happen in this model. Super interesting outcome. Experiment 2, reaction time was increased during invalid Q trials. Reaction time is decreased in valid Q trials. This holds true to human studies, and we will go over why here in a little bit. And then experiment 3, and experiment 3 is just the coolest experiment, and the demo goes through a lot of different trials of experiment 3, and we go through it in a stepwise fashion, so you can see what's happening at and really it's every 10 milliseconds. You can see what's happening in the model, the activation throughout the neurons every 10 milliseconds in a trial. And we can go through in a stepwise fashion and pause wherever we want. So I definitely recommend checking that out. So a standard AB was observed in same stream trials, which we would expect, and that's what happens in human trials. So when both targets are presented in the same stream, you get a standard attentional blink. Lag 1 deficit was observed in different stream trials, again, just like in human trials, and then bringing in lag 0 trials, I did see lag 0 sparing in the model. And what's interesting is lag 0 sparing in the model, that when we analyze it from an activation standpoint, because of course in this model I'm not asking the model to report target identities. What I'm doing is I'm looking at the level of activation associated to those target identities. So when I look at the activation associated to target identities in lag 0 trials, what's really interesting is I see dynamics that are comparable to fMRI studies looking at activation levels for competing stimuli in two different competing targets in two different spatial locations. Very interesting. And that's another route that I want to go with this model. So let's see what let's get this on to some charts if you're a more visual individual. So here we go. Simulation results. Let's go to experiment 1. This is outputs from the model. So we're looking at activation levels here. These are just arbitrary numbers. And if we look at it in relative to T1, so this is the activation associated to T1, and this is the activation associated to T2 when presented at lag 1, lag 2, lag 3, lag 4, lag 5. And we see clearly there is a degree of lag 1 sparing, comparable to later lags. Extreme deficit at lag 2, lag 3, starting the recovery, and then we recover out to lag 5. Now, of course, this isn't the percent of correct responses, because I'm not measuring that in this model, but if we add variance to the model, and say we have, bars showing our variance, so lag 2 would be at, 3.75 activation plus or minus 1, and lag 3 would be, 6.5 plus or minus 1, and we have these bars, and there was some kind of a threshold here. The amount that bar goes over that threshold would be analogous to a percentage of accurate report. But we don't need to do all that. We can clearly see there's an attentional blink here just in the activations. So I didn't go that further step. I really don't think it's necessary. In other studies that do computational models of the attentional blink don't do that either. So, but I am by no means an expert. So please, if you think there's a better way to interpret this, you won't hurt my feelings by telling me. It will help me immeasurably. Experiment 2, we're looking at reaction time. Now, of course, there's no reaction time in my model. It's just it's just level of activation. So I have an interpreted level of activation as a relative response time, assuming that a higher degree of activation will be responded to quicker in working memory than a lower degree of activation. And so what we can see here is, following suit with Mike Posner's study in 1980, in valid Q trials, the relative response time is much lower than in invalid Q trials when compared to a neutral Q condition. And then looking at experiment 3, which again was just the coolest experiment, tying it all together, we see lag 1 sparing in same stream trials and lag 1 deficit in different stream trials, and then they tend to recover in the same way out towards lag 9. Now, what's interesting here is, one thing, if you're looking at the Jeffries 2017 study, this is analogous to the 100 hertz experiment. So they did this experiment in many different, not 100 hertz, 100 millisecond stimulus onset asynchrony. And they did a lot of experiments at different SOAs, and I didn't go into that at all with this model. This model was built. This is a 100 hertz model, so it kind of limits me in how I can present information or inputs to the model. So I focused on that 100 millisecond SOA trial, and this actually looks identical to what they observed in their study. So super interesting stuff. All right, so now we're going to go through real quick how we might interpret coalitions from the model. This is a really good time first to go and pause this presentation, jump over to the demo if you have time, if you're curious in how this model actually works. It's going to make a lot more sense. What we're about to go through is going to make a lot more sense if you do go and see that demo. Of course, it's not required because none of this is required. And for those of you that are still watching and listening, I thoroughly appreciate your time in looking at this. It is definitely an act of charity. So, but this would be a good time to go check out that demo, and then we're going to jump into how to interpret coalition strength and coalition dynamics from the model itself. Okay, so the really cool thing about SimBrain is that it allows us to record unit activations at every time step within the model. So what I can do is record, I can pull data for every single node in the network, every single neuron in the network, or pick which ones I want to record, and I get a full output of what their activations were at every single time step, so every 10 milliseconds in the model. And this is super helpful for understanding coalition strength. So what I've tried to do is model this concept of an object dimension and a location dimension and the dynamics that make up the two. And that, of course, became what I'm calling perceptual coalitions. But how do we understand the dynamics of a coalition? So really what we're looking at here is the life cycle dimension of coalitions. And in this case, we're looking at the location dimension. This is data pulled from experiment 3 with T2 being presented at lag 3. And this is a different stream trial. So we have T1 is presented to the left side of the network, and T2 is presented to the right side of the network. And what we're looking at are the coalitions, the location-based coalitions corresponding to those sides. Right? Now, the idea of a coalition is it's not a concrete thing. There is no coalition neuron in the network. So how do we How do we interpret this? And so this focusing network should be familiar to you. We saw this earlier. What this graph is showing us is the summation of the outputs, or not the outputs, the activation of a focusing exciter and focusing inhibitor pair. And that's what I've taken to determine as the strength of the coalition in the location dimension, right? You might think of it as also the degree of specificity of that dimension. So, right, what we're looking at here is the zoom lens model. This is kind of, and it's an abstract interpretation, but it is in fact the zoom lens model of attentional focusing as implemented by this focusing network. So you can look at this, we can look at this in terms of temporal dynamics. How long does it last? What factors go into its decay? What factors go into its creation? And then if we look at it in the vertical direction, this is degree of specificity, right? So when it's at its peak right here. This network is extremely focused on the left side of the visual field, right? So T1 is presented here, and by lag 1, between lag 1 and lag 2, what we see is that the attentional focus has shifted completely to the left side, right? And so to break this down, what this point means is that there is a huge degree of activation in this exciter, which is feeding inhibitors, which we can see here. So let's say I'm pulling from these two, that's the blue line, and these two, that's the red line. So what we're seeing is a high degree of excitement in the left side, leading to a high degree of inhibition in the right side. And that's represented in this graph. Now there's almost no degree of, really in this case at lag 3, there's no degree of inhibition to the right, or to the left side, right? And that's why this is so high. So what we see here, this delta between the left and the right, we can think of this in terms of that spotlight being very constricted to the left side of the visual field. Now, as the input from T1 stops, now we enter into this phase of decay. This coalition will die. There's nothing maintaining this coalition. The task, when we think about bottom up, the bottom up activation from T1 has ceased. It's gone. Now in this task, it is not specified which visual field, or which side of the visual field, which stream the targets will appear. So there's no top-down activation keeping it focused on the left side. So in the absence of that bottom-up activation, this will begin to decay, and that's where that exponential decay comes into play, right? Now, as it decays, it will send less activation, or it will send less activation to these inhibitor neurons. And so you'll see the inhibition on the right side decrease. Now, T2 is presented at lag 3. It's presented at a time where there is still some inhibition on the right side where it's being presented. So T2 is being presented to the right side of the network. There is still some inhibition present because there is still some residual activation still in play. And you can see the exponential decay happening here. It's not a linear decay. So there's still some, this coalition around the left side is still a little bit present. So what we can think of here is the spotlight of attention is still a bit focused, or still favoring the left a little bit. It hasn't completely opened up to bring in the right side. Now, because of this lower degree of inhibition, when T2 is presented at lag 3 in the opposite stream, it is able to start to form its own coalition. But you'll notice that this coalition is not as strong as the coalition at T1, and that is because of its starting point. It had to fight first. So a lot of its energy, a lot of the assembly phase was geared towards shutting down this other coalition, because it has to shut down the other coalition to form. And then you see it will rise, and as it rises, it will institute some inhibition to the right side, and then we'll decay away. And what that equates to in the experimental outcome, and let's go back to here, is a reduced ability to report T2 at lag 3. That's what we're seeing right here, right? But it is better than at lag 1, because if we go back to this diagram here, if I present T2 at lag 1, I'm presenting it to an already forming, an already very powerful coalition in the other side of the visual field, right? This portion of the coalition is the strongest portion, really. Once you get halfway here and up, that is the strongest portion of the coalition. So when lag 1 is presented there, there's just no chance. So that's where you see lag 1 deficit in different stream trials. So I hope this makes sense. This is how I'm interpreting coalition strength in the model, and I think it's a pretty logical way to do it. It makes sense to me. Hopefully it makes sense to everyone else. If you have any other ideas of how we might better refine this idea of coalition strength within the model, I would absolutely love to chat about it. It's super interesting to me, and I'm always finding new ways within this model to interpret things and find new ideas. So I would absolutely love the help. Bear in mind, so we're talking about location dimension here. This focusing will also occur in the object dimension as well. I don't have graphs for that because in my simulations I did not have competition between different types, right? So the target type, not necessarily the target identity, but the type, so digits versus letters. The target type was always determined by the task, right? So in all of those experiments, the target type is determined by the task. But we do see coalition strength affecting attentional focusing in the object dimension when it comes to focusing further down from type into individual type identities. So like the letter or the number 3 as opposed to the number 7. And we're going to jump into that now. Okay, so when we're looking at the object dimension, again, going back to the structure here, I've modeled this a little bit different. So this final phase of object focusing down to an individual digit, let's say in this case, an individual digit. I've modeled it with these modulatory pairs. Again, I can do that with focusing networks. I can do all of this with focusing networks. With the amount of units, and you'll see in the network, it was much easier to do it this way, but they are modeling they're simulating a similar concept here. And we can see, just like with, and what this graph is showing is the interaction of these two, right? The amplifier unit and the suppressor unit. If I compare their activations, basically taking the activation of amplifier units and subtracting the activation of suppressor units, I get this curve, right? And then this is in response to a single stimulus presented to the network. So this is not from RSVP. This is just a single stimulus presented for 70 milliseconds. And just so that we can see what that dynamic is. And what happens here is you have a scenario where a stimulus is presented and both of these units become active. And they're about on par with each other. Now, in my model, I've altered the decay coefficient in the amplifier node to decay a little bit quicker. So what happens is you have this delay, and essentially what that equates to is a delay in focusing. So a target is detected, and that target has a specific identity within that type bundle. Well, the whole of that type bundle will become kind of primed for new activity, right? And there's that delay here. If I were to present another target within here, it would be detected. Now, what happens is this type bundle will begin to focus in on that individual object, and it will focus until it reaches the height of focusing, because that stimulus input has receded. It's ceased. So you'll reach a height of focusing on that individual identity, that individual object, and then that focusing will begin to decay back to include every object in that type bundle. Right now, the shape of this should be familiar to you. This is the attentional blink, right? So this is a shadow of the attentional blink. And we can go back real quick and take a look at that. What we're looking at here is, again, so it's almost as if doing RSVP studies on humans is analogous to X-ray crystallography, right? And we've cast a shadow. And so we're seeing those dynamics. So when we look at this model, where are the control mechanisms? So of course the short answer here is that there are none. I don't believe that these focusing networks equate to a control mechanism. They're just a structure that exists for coalitions to compete with each other. They're facilitators, not managers, right? So in this view, attention exists as an emergent artifact of coalition competition, and it's an outcome of these dynamics. So if we look back at the previous slide, the attentional blink in this model does not arise out of some kind of a cognitive strategy. It doesn't arise out of anything other than the object dimension going one layer deeper, focusing on based on these Gestalt principles, right? So because the model has focused on the individual identity of the target, that creates this deflection in attention, or really this focusing to a deeper level that will then exclude T2. Interesting. So that's that emergent aspect. It doesn't seem logical to me that there is a control mechanism creating attentional dynamics. In alignment with the bias competition model, this competition of coalitions is fully biased by top-down and bottom-up inputs, right? There is no selector, there is no controller. It's just a blending of top-down and bottom-up inputs. And so I understand you might be thinking in your head, this is just all semantics. The top-down influence is the control mechanism. I have a completely different take on this, and I go through it in the draft of a paper that I've written up. At the end of the discussion, I go a little bit beyond the implications that these perceptual coalitions have on attention, and go into consciousness and phenomenology, and kind of create a mechanistic equation very similar to field theory that would explain what these top-down inputs are, and that it is a wholly feed-forward kind of like an animal behavior. You have a stimulus-response contiguity, and that's really what I believe is happening here, and that can be explained in terms of these coalitions. and in the ways in which these attentional dynamics and working memory dynamics interact. And that's, I think, it might be a part that I exclude from the paper and look at down the road, but in my opinion, it's the most interesting aspect of it. So definitely look into that. So here's another big question. Is attention episodic? And in terms of this model, the answer is no. And again, you might be thinking, well, this is semantics, but so observed episodes in this model are the artifacts of coalition dynamical dimensions, right? So we're looking at life cycles of coalitions, not the creation of distinct episodes. So in this model, there is no blaster that is creating, starting and completing episodes. Episodes themselves are not the strategy at play here. It's just an emergent outcome of essential nodes and coalitions competing for representation in working memory that creates this seemingly episodic nature. In my opinion, it's much more wave-like, and what we're seeing in the attentional blink is basically this modified Gaussian dynamic of a coalition life cycle, right? So T1 generates a coalition, and RSVP is the perfect protocol to highlight the shadows of that modified Gaussian life cycle of that T1 of that coalition associated to T1. Spreading of sparing and lag 1 sparing, rather than these being objects or stimuli that are brought in with an episode associated to T1, rather what it is that the presence of T2 of a different identity. So a target, so let's say T1 was the number 3, T2 is presented immediately after, and it's the number 7. What that does is it stops the object dimension of the coalition from focusing any further beyond digit, right? Now, in the absence of a second target, that object dimension will hyper-focus on T1's identity. When you follow it up immediately with another target of a different identity, it keeps that focus at the level of type, right? So it prevents that hyper-focusing. And that's why you get lag 1 sparing, spreading of sparing. Now, when you're looking at temporal swapping in the report, now that probably has something to do, as is suggested in the ST-squared model, with a handoff to working memory, right? So there's something at play there, and I'm not looking at that in this model. I want to focus specifically on attention. That thus would not be a dynamic of attention, but it would be a dynamic in that binding process, right? And I'm not particularly interested in that for this model. Of course, that is a future avenue by which we can explore this concept, and it's something that I want to look at. I want to look at the interaction between the kind of the birth of these coalitions in what we call attention, and how they form higher level working memory coalitions, right? So that's future avenues. But the question, is attention episodic? I would say no. We're looking at the modified Gaussian life cycle of coalitions, and this illusion of episodes is an emergent artifact of that. So getting back to this debate, is attention the result of limited cognitive resources? And again, like I've said before, I'm not impressed with those accounts. It just doesn't make sense to me why that should be should be necessary. I can understand the illusion of limited resources, but I don't understand what an attentional resource is. How do you quantify an attentional resource? Instead, it seems pretty clear to me that there are plenty of resources. So if you look at spreading of sparing, all of a sudden this perceived deficit, the deficit is gone. So that would suggest to me that there are plenty of resources to report all of the targets within an RSVP stream, or report every object in a visual field, but we don't. So I want to reject those limited resource accounts because they're at odds with evolutionary game theory, and these are, of course, biological systems that arose out of natural selection. So we would be wise to listen to the suggestions of evolutionary game theory. Now, we know from evolutionary game theory that veridical perceptual representations of reality would be driven to extinction in the presence of utility-based perception, right? Now, this model provides a mechanism for that. It explains how those beneficially limited representations of the environment might arise in an emergent way without a control mechanism. So, what is that mechanism that's at play? And the mechanism that's at play in this model is extremely simple. That's these perceptual coalition dynamics, right? They're perceptual coalitions. We know they have a focal width dynamic. They have a life cycle dynamic. Within that life cycle dynamic is the assembly phase, the phase of intense competition with other coalitions, and then a decaying phase. And it's because of that intense competition that you only get, in the case of this model, one coalition is going to be active at a time, and it's going to exclude everything else. Now, it's the coalitions that are active it's not random. This is not a random process. It's a simple math problem of blending top-down and bottom-up activation, right? And so by blending top-down and bottom-up activation, you can get an extremely utilitarian recreation of the environment that I would suggest would be extremely evolutionarily beneficial. So think of it as a beneficially limited recreation of an agent's environment. And this is a mechanism by which that can be achieved without control. There's no control in the system, which to me, we keep looking for control mechanisms in the brain, and we're not finding them. And that's because, in my opinion, that's because they don't exist. It's very, very rare for natural selection to produce centralized control. It just, that's something more akin to a designer, and I don't find arguments suggesting a designer to be particularly convincing. I hope I'm not offending anyone, but it seems ridiculous to me. So we know what evolutionary game theory is telling us. We know what empirical studies are telling us. And this is a mechanism by which both can arise emergently. And I find that to be very powerful. All right, for those of you that have a draft of the paper that I'm trying to write, you'll know that the second half of you'll see that the second half of the discussion is pretty rife with speculations. And that, that's partially because this is all theoretical, and where would theory be without speculations? But that's just largely because I haven't had the time or resources to simulate everything here. And if I did, this paper would be even more enormous than it is. So, but there are other attentional phenomena that I believe can be explained in terms of these perceptual coalitions quite effectively. So if you look at binocular rivalry, monocular rivalry, the Necker cube, and other cases of multi-stability. So for instance, the vase and faces, silhouette faces photo. Those are a great opportunity to dive into the competition between competing coalitions, right? Where the bottom-up influence remains at a constant, but there must be some form of competition happening in perhaps working memory level coalitions, and that only the winning one will be able to send that top-down bias, and that's why you get that perceptual flip back and forth. Inattentional blindness is a absolutely great way to look at top-down bias and top-down maintenance of coalition life cycles. So in the classic case of, count the basketball passes between players in white shirts. That's a fairly intensive, difficult task for an individual to do. And so the top-down activation that's feeding into the coalitions that represent the basketball and the white shirts are very strong and maintained. And they're maintained to a level that the bottom-up activation of the gorilla, and this must sound really weird if you're not familiar with this study, but check it out. I think the paper was Gorillas in Our Midst. Like late 90s, 1999 maybe. But anyway, super interesting situation. But the bottom-up visual input of the gorilla walking around the scene is not enough to override the coalitions that are task-related. So that's a possible way to interpret that particular study. Visual search. I've got some really cool diagrams on how I believe, based on the empirical data, the zoom lens model works and how it moves about the visual field, much like an inchworm. So I definitely recommend you go and check out those diagrams. And then contingent visual capture is another one. So a study done by Charles Folk at Villanova demonstrates some of the abilities, even when the spatial location of targets is guaranteed by the task set. Adjacent visual distractors that match some portion of the target set. So let's say, targets are going to be digits, red digits. Red digits are the target, and it's guaranteed that they will appear at the fixation point. If there is a red letter placed outside of that fixation point at some point within the visual stream, it can induce a blink. The paper is called Made You Blink, is the first part of the title there. So, and that's a very interesting one. But that can also, I go through in the paper how that can be explained in terms of coalitions. Moving forward from just attentional phenomena, but how do we explain individual differences? I mentioned earlier that a main goal of this project was to provide a mechanistic explanation of the possibility of individual differences. So there, and if you go through my model demo, I talk a lot about decay coefficients and just small alterations in decay coefficients throughout the model, which would equate to the leakiness of a neuron cell membrane, which obviously has a genetic component to it, which of course makes it a candidate for variation in natural selection. It also can be a mechanism of variability from individual to individual, which we know occurs naturally in a population of individuals. There's this natural variability in genetic traits. And so looking at that's definitely a possibility and a possible avenue to explain individual differences in attentional tasks. When you look at mindfulness and mental training, this is kind of what my background was getting me into this particular arena. When people are, when individuals are trained for, I believe it was a period of 60 days, they were trained in mindfulness meditation, they showed a reduced temporal duration of the attentional blink when compared to a control group. We also, there's a lot of studies that are looking into why that might happen. But one way in which I've actually kind of modeled this already, I haven't formalized it, but I've simulated this. If I reduce certain, if I increase the amount of decay in certain units, particularly in the suppression units of modulatory pairs, but also I can do the same thing within the focusing networks. But if I increase the decay or the leakiness of those neurons, I can create a reduced attentional blink in the model. And so that would actually coincide well. So increased decay rate in those suppression units would mean a reduced period of competition within those coalitions, and would equate to a reduced lifespan of coalitions, which coincides with kind of the qualitative description of a reduced tendency to hold on to thoughts or hold on to certain stimuli in trained mindfulness meditators. Of course, it's all qualitative and speculative, but it makes sense. So I really want to dive further into individual differences. I think that's super interesting. It's just a super interesting thing to do. For instance, we can, one avenue by which we can validate this model is, let me simulate the effect of increasing that decay in suppression units to create that reduced attentional blink, and then see what impact it has on the other two studies, so dual stream RSVP and spatial cueing tasks. And then we can go and train people in mindfulness meditation and run them through those tasks as well, and see if we get the same outcomes as we do in the model simulations. So the opportunities there are endless and are very interesting to me. Of course, I don't have the capability, the facilities to do those studies with human subjects. So those possibilities will have to reside in someone else's home. But it's very interesting to me. And then this idea of this feed-forward stimulus-response contiguity that I kind of talked about before, relating to animal behavior. This idea that coalitions in attention elicit coalitions in working memory, and working memory coalitions feed back in the form of top-down activation. I have formalized this a little bit more in the paper, so I definitely recommend you look at that. I believe it's the last section of the discussion, where I kind of relate this to field theory. Field theory being the idea that behavior is a function of the person and their environment, right? So you have a mathematical relation between the two. And so I've kind of done a similar thing, but instead of doing it as a static equation, I look at it as a time series. And, you'll see it in the paper. It's definitely interesting and worth looking at. As far as future work goes, I definitely want to build more robust model simulations. I think that this one has been a good starting point, but there'll need to be a lot more simulations and models to kind of further understand what I'm kind of calling here this perceptual coalition theory of attention. And again, I do believe that it will go farther than attention, but more models need to be made. Along with that, I do not believe that this process of coalition dynamics and life cycles does not pertain only to visual attention. I chose visual attention because it's more thoroughly studied than any other modality, but I do believe that perceptual coalitions will prove to be multimodal and that they will interact. So modalities will interact. And again, introspection would support this. We all know that paying attention to something visually can make you forget that you're listening to music, or that all of these or a loud sound, a salient sound will direct your visual attention in a certain way. So they do seem to interact, and I would like to investigate that interaction. Also, I want to investigate the connections between attention and other systems, right? So kind of this idea down here, how does the outcome of attention, or this formation of perceptual coalitions, feed forward into working memory? How does emotional valence, we know, has an impact on attention? How does that feed in arousal, motor control, all of these things? And then we can really start to get a very, very mechanistic, have a very mechanistic approach to cognition. And then what I'm ultimately extremely interested in is the philosophy of phenomenology. And how can we apply this framework to the mapping of brain states that elicit consciousness states? Jeff Yoshimi, the creator of SimBrain, has some really interesting papers on these concepts. And that's a little bit off in the distance and kind of hovering out in left field compared to this, but it is ultimately what I'm very interested in, and I hope that I can eventually build a framework that helps to have a more mechanistic approach to phenomenology. So anyways, that's all I have here. Kind of weird to say that's all, because I'm sure this is an insanely long presentation, but if you listen this far, I do appreciate you listening to it, and I hope this helps in understanding what it is I'm trying to write down, and maybe helps helps in teasing everything out. So thank you for watching and listening, and let me know if you have any questions, and reach out. I'd be glad to chat, phone, Skype, email, whatever works. Thank you.